Assalamualaikum and hello. We're from Team 6 and we will be presenting how do scalar and vector potential apply in electromagnetic field. This is our group members. Me, myself, Dayana Nhatasya, MARCELL JUDITH Paul, Muhammad TAUFIQ bin PODANG, and SYAHIRRA binti MATSAH. This will be the problem statement for our topic. First of all, what is the difference between a scalar and a vector potential in an electromagnetic field? Second of all, what are the applications of scalar and a vector potential in the electromagnetic field? Lastly, the third one is, what is the mathematical relationship that exists between scalar and vector potentials as well as the electromagnetic field?
Okay, firstly for the objective, to explore and provide a comprehensive explanation on how do scalar and vector potential apply in an electromagnetic field, which means how do we apply scalar and vector and what use of them in the real life. Secondly, to investigate the mathematical relationship that exists between scalar and vector potential as well as the electromagnetic field, which means we do calculation on how do we use scalar and vector potentials as well as the electromagnetic field. For the hypothesis, the manipulation of scalar and vector potentials in electromagnetism will have a demonstrable impact on resulting electric and magnetic field. By exploring different gauge, we hypothesize that certain gauge transformation will simplify the mathematical description and contribute better understanding of electromagnetic event, which means here when we do calculation on the manipulation of scalar and vector potential in electromagnetism, we can see or we can demonstrate the impact on resulting electric and magnetic field. And then by using different gauge, we can see that certain gauge transformation will simplify, or it can help us to understand easy and contribute better understanding of electromagnetic events.
Next, we will go through to the analysis of information of data. So, scalar and vector potentials are important concepts in electromagnetism that help to describe the behavior of electromagnetic fields. So, let's analyze how they apply in the context of an electromagnetic field. So, the scalar potential is often denoted as V, which is a scalar field that represents the electric potential energy at a point in space. So it is related to the electric field through the gradient of E, where in this equation E equal to negative nabla V, which is the nabla represent the gradient operation. So the next one is vector potential, which is denoted as A, which is a vector field that is primarily used in the context of magnetic fields. So it is related to the magnetic field B through the curl of A, where you can see the equation at here, B equal to nabla times A, which is nabla represent the curl of operator. Next, we move to the finding, which is the scalar and also vector potential in electromagnetic field typically involve solving differential equations based on the given source of electric charge and current. So the procedures varies depending on the specific configuration of the electromagnetic system and the boundary conditions. So first we look to the scalar potential V, which is it has Laplace and also Poisson equation. So the Poisson equation links the charge distribution with the scalar potential, which is V, and the Laplace equation holds for systems with no free charge. So in scalar potential, there is also boundary condition. So the use of suitable boundary condition to solve the Poisson or Laplace equation. So the problem shape and the potential behavior at various positions in space determine the boundary conditions. So how to determine the scalar potential? So the scalar potential or V for each point is in space can be obtained by solving the Poisson and Laplace equation with the specified boundary condition. So there's application in Laplace. First one is in electrostatic, which is in the absence of free charges, the electric potential satisfies the Laplace equation. Second one is heat conduction. In steady state heat conduction without sources, the temperature distribution is governed by the Laplace equation. As for the application in Poisson equation, for the first one is in electrostatic. In the presence of free charges, the electric potential is determined by the Poisson equation. As for the semiconductor physics, the Poisson equation is crucial in modeling the behavior of charge and carriers in semiconductor. Next, we move to the finding of vector potential, which is A. In this vector potential, they use the Ampere's law with Maxwell's addition. So the vector potential A is related to the current density J by the equation. So this is a wave equation that includes both spatial and temporal derivatives. Choosing gauge conditions in vector potential are also crucial because different choices of gauge conditions can simplify the calculation. So there's two common gauge, which is Coulomb gauge and also Lorentz gauge. So first thing, we look at the Coulomb gauge, which is its condition is nabla times A equal to 0. So in this Coulomb gauge, the advantages of this column is simplifies the wave equation for the vector potential, making it more easier to work with. And the physical interpretation is this gauge condition ensures that the divergence of the vector potential is 0, which is analogous to the electrostatic condition. Next one, we look at the Lorentz gauge condition. So the condition is as stated below. So the advantages of this Lorentz gauge condition is maintains the symmetry between the electric and also the magnetic fields. So the physical interpretation is ensures that the wave equation for the vector potential is consistent with the wave equation for the scalar potential and also satisfies the relativistic invariance.
Hello, my name is SYAHIRRA binti MATSAH. I would like to talk about the implication of the how scalar and vector potential apply in electromagnetic field. Electromagnetic theory, essential in electrical engineering, focus on the study of changes in motion and ethers. Understanding and designing various systems require knowledge of this theory, often extended through circuit theory. Vector analysis is crucial in explaining electromagnetic concepts. Scalar and vector potentials derived from the Maxwell's equation simplify mathematical representation, aiding in the analysis of complex problems, while the Gauss freedom enhance computations and vector potential application in electromagnetic wave are vital. Then the implications of potential extend to scientific, technical, and practical domains, simplifying equations and allowing for the separation of variables in Maxwell's equations. While the engineering applications benefit from potential, understanding the influencing the design of the electric circuits, motors, transformers, and communication systems. Well, the potentials are fundamental in quantum electrodynamics, particle physics, and advanced technologies like medical imaging, MRI, and electromagnetic wave propagation for radar and telecommunication. Well, fundamentally, electromagnetic fields understanding through scalar and vector potentials, which it contributes to a better comprehension of nature's underlying forces, making field theory essential. That's all. Thank you.
Now we have come to the conclusion. In conclusion, understanding electromagnetic fields requires mastery of scalar and vector potential. Scalar potential simplifies the characterization of electric fields by ignoring direction, while the vector potential is crucial for comprehending magnetic interactions. This potential play a key role in developing technologies like electric circuits, quantum physics, and MRI. Simplifying mathematical represents and contributing significantly to science and technology advances. That's all from us. Thank you. That's all from us. Hope to see you again next time. Thank you. Bye bye.